Okie dokie, guys. Oh gosh, that's really annoying. I hope I can ignore that. There's a little bit of an echo as I'm trying to record this. So if I sort of stutter and stammer, that's probably why. I mentioned the email address, the blog. Let me go ahead and, it's probably better that I do it that way. That way I don't get any feedback from the audio. I mentioned the fact that I had set up sort of a web presence for our Fun with Math together. Just to be clear that everybody knows, Virtual Fourth, which actually, when I was discussing it by email with a couple of y'all's parents, actually popped up in one of their emails. I forget which parent it was, but they said Virtual Fourth is great. So I was like, that's pretty clever, Virtual Fourth. So virtualfourth at Gmail, virtualfourth.wordpress.com, and at virtualfourth. And of course, through the Twitter feed, I will announce, when new blog posts are up, when new videos have been posted. But I will also, as I'm so oft to do while I'm lecturing with you guys, recommend books in terms, especially ones related to mathematics. In fact, I just got done with one that was actually pretty neat. It was very The Joy of X, which was, of course, a play on words. But it was really neat. It was like 27, 28 short chapters, sort of running through and trying to make it sort of fun. He even uses some of the same imagery that I used in some of my lectures, and he had a very playful style. And the Kindle version was like, I think, less than $1. So that's kind of why I got it. We don't have a car here, so I actually ride the bus a whole lot. And riding the bus, I have a whole lot of time to pull out my Kindle on my way to, go up to the school and go to my office and study and whatnot, or go to the library. So, but I digress. Y'all really don't want to hear about that. But you may actually want to hear about that. Yeah, it's ugly here. Yeah, that was actually the view of the coastline when I went to go visit one of the medieval castles, the ruins of a medieval castle called Castle Dunatar. So yeah, it was just breathtakingly ugly, and I couldn't stand it. And I'm just so distraught that I made the trip across the pond to such an ugly place. But I digress. Let's go ahead and get started talking about limits. And unfortunately, you know how I never really read from the book, except for an occasional recourse to tell you about a definition or a particular theorem or something like that. Well, as much as, like I said before, I don't like teaching to a test, the AP exam will actually ask you about some of these theorems, some of these definitions, and so it actually does us some good to go ahead and talk about some of those. Now, this is, of course, 2.1 in your book. It ought to look very, very familiar if indeed you have opened up the book and taken a look at it. And like I said in the last lecture, you should. And it starts out 2.1, and I think this is great that Stuart does this. He does what I did in the last lecture. He explains to you why it is that you're going to learn about limits by introducing the tangent line problem right from the get-go, and that's really great. But what he does, that's also good stuff, is in 2.2, he goes ahead and tells you the definition of a limit. Suppose f of x is defined when x is near the number a. This means f is defined on some open interval, parentheses, not brackets, that contain a, except possibly at a itself. Okay? And so basically that's saying when a number is sufficiently close to x, right? Then we write the limit as x approaches a of f of x is equal to L. Okay? If we can make the value of f of x arbitrarily close to L, as close to L as we like, by taking x to be sufficiently close to a on either side of a, but not equal to a. Now, I think I showed y'all last year the delta epsilon proof of a limit. All this is really saying in terms of all this verbiage is saying is that if I have a curve, okay, and I'm dealing with a limit, right, and I want to figure out how to get the limit as x approaches a, right? And you know that that limit is going to be this value right here, okay? Not f of a, but L, okay? So basically, it's saying that the limit exists at L as x approaches a if I can, by some manipulation, get the output sufficiently close to L by getting the input sufficiently close to A. So basically, as I narrow in towards A, I will narrow in towards L, and that's all it's saying. But notice that it is not talking about equality, right? And this is one of those things where at the end of last year, and just like, you know, when Tim wanted to cancel terms rather than factors, or whatever mistake he made that I jumped up and down and screamed about, I jumped up and down and I screamed, approach, 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 okay? Limits are not about equality. In fact, this function need not exist right there. It could be a removable discontinuity. I do not care whether the function exists at A. I do not care if there's an actual f of a value. I care, as I'm approaching it from either side, what the value is approaching. So as x approaches a, is what number is f of x approaching, if anything? And of course, like we talked about last year, in order for the limit to exist, the limit must be the same from the left and from the right. And in this case, it actually is, okay? This case, this is a function that is continuous, except for possibly at a, and therefore the limit does exist there. But remember, that's why it has right here, where it says, this means, in the parenthetical right here in this first and second line of the definition, right here at the end of the parenthetical, except possibly at a itself, okay? That means that it can be undefined at a, meaning that an f of a value and an output value for the mathematics of equality may not exist. But we do know that as long as it's approaching the same L value from either side on the output, when we approach the same A value from the input, then the limit exists. Okay, and that's all that that's saying. And I might even go ahead and show you the Wolfram demonstration, the animation that shows what I've termed the delta epsilon proof of limits. But since, and I don't think that they've changed this, they have since eliminated delta epsilon proofs from the AP exam, and I really don't find delta epsilon proofs to be all that helpful, and I can go in later to the whole history of why they arose historically to begin with and all that sort of jazz. But basically all you need to know is the whole language of sufficiently close as we approach, okay? Now, we're going to get into the analytic, meaning the notational aspects of solving for a limit or evaluating a limit later. But I just wanted to sort of go through here and just highlight the purple boxes and deal with those before I basically open up last year's test, okay? Now remember when I said that the limit must be the same from both sides. Now, that doesn't mean that we can't talk about limits from one side or the other. It's just that when we talk about limits as such, it's assumed that we are talking about limits from both sides. But let's go ahead and enlarge this just a little bit so I can sort of focus in on this. Okay. So notice right here, down in this notation right here, okay? And it's not doing a very good job of highlighting. But notice right here, it says as the limit as t approaches 0, and it has a little superscript right here that's a negative sign, okay? That negative superscript means from the negative side, okay? So obviously on a number line, anything to the left would be from the negative side. So if I'm approaching 5, 4 would be on the negative side of 5, even though it's not negative in and of itself, right? And so basically, as t approaches 0 from the left, and left negative side, however you want to think about it, but obviously the left side and negative side are synonymous with each other, just if you think about the number line. Okay, and limit as t approaches 0 from the positive side, you put a little positive superscript right here, okay? And basically that allows us to talk about one-sided limits. So here in the definition number 2, we write the limit as x approaches a from the left, or the limit as x approaches a from the negative side of f of x is equal to L. And we say that the left-hand limit of f of x as x approaches a is equal to L. Now, the actual limit as such may or may not exist, but sometimes it's helpful to have that notation such that we can describe a one-sided limit if we actually want to, right? If the circumstances arise that makes it sort of a good and prudent thing to do. But here we see the fact that the limit as x approaches a of f of x is equal to L, here in the red little box, definition number 3, if and only if the limit from the left side and the right side are the same. Okay, and we'll go ahead and get into that here just a little bit. The last thing we want to talk about, at least I think it's the last thing, are infinite limits. Now, there's a difference between infinite limits and limits at infinity in some books that it gives you. Some books sort of shove them into the same section and call them limits involving infinity, okay? But sometimes, and this is kind of what I was taught, so this is the way that I actually do it. Limits at infinity deal with the actual input value. So the limit as x approaches infinity of f of x, right? Actually, no, this is infinite limits, I think. And the thing is, it really doesn't matter. But the limit as x approaches a of f of x, if that's equal to infinity, then that's an infinite, then that's a limit at infinity or something like that. But basically, some teachers have a way of distinguishing between limits that have infinity as the sort of input approach and limits that deal with infinity as the output approach. And of course, limits like this, where x approaches infinity, or indeed negative infinity, we know this. This is our old friend n behavior, right? This right here has to do with asymptotes. Okay, so this has to do with as x approaches a finite number, it goes off to infinity or negative infinity along an asymptote. This has to do with going along a horizontal asymptote. Is there a recognizable end behavior? As you go off, is there a recognizable end behavior? Is there a horizontal asymptote, or is there not? Okay, you're just going to need to ask your teacher whether she distinguishes between the two, and if so, what she calls each of them. Okay. One further thing that we need to talk about is that when actually, let's go ahead and look at some of this after. I think this is the end of it. Yeah, okay. Well, let's go ahead and look at this one right here. I've gone ahead and imported y'all's test from last year. Now this is has to do with analytic stuff. This is properties of limits, but we'll get back to that. What I really want to focus on right here was this graph, okay? Now you've seen this graph before. This is actually your test from last spring. But notice what we're talking about here. Okay, the limit as x approaches 2 okay, is what? The limit as x approaches 2, which, oddly enough, I've actually asked right here. The limit as x approaches 2 looks like it's 3, okay? Or somewhere right around there. It's approximately 3. But notice that the function actually exists there. Now, does it have to exist there? No, it doesn't. It doesn't have to exist there. But the limit as x approaches 2, okay? And actually, let's go ahead and... it's actually shrunk it down. Let's go ahead and put that right there. And let's go ahead and pull this over. See if we can set this side by side. Okay, now the limit as x approaches 2, notice that the limit as x approaches 2 of f of x, if f of x is defined by this graph, is 3. Now, f of 2 is equal to 3. Coincidence? Not really. The function is continuous there, okay? But need this be the case? No, it doesn't have to be the case, okay? So let's go ahead and look at another question that I've asked. The limit as x approaches -8 of f of x. Now notice that the limit as x approaches -8, am I worried about this point right here at -8, -3? No, that's the mathematics of equality. That's the actual function value at that point. I'm not worried about that because if I'm talking about limits, I'm actually sort of hiking along this path, approaching this point right here. Okay, so the limit as x approaches -8 is actually -6, even though the function value is -3. Okay, as x approaches, as x approaches -8, f of x approaches -6. But at -8, f of x is -3. Okay? But here's the thing. That limit would be the same if that value right there didn't even exist. That value right there doesn't even need to exist. The function doesn't need to exist at that particular input value in order for the limit to exist. For the limit to exist, it simply needs to approach the same output value from the left and from the right, from the negative side and from the positive side. Okay? Now, let's talk about the limit right here at x is equal to 6. Another question that I asked. The limit, and we'll sort of put that in braces so we can sort of section it off. The limit as x approaches 6 of f of x actually does not exist. Because if you approach 6 from the right, from the positive side, the output values are approaching 5. If you approach it from the left-hand side, the output values are approaching 2. Well, since the limit as x approaches 6 from the left of f of x is not equal to the limit as x approaches 6 from the right of f of x, those two values have to be equal for this to have an actual value. Since these are not equal, this one's 2 from the left, this one's 5 from the right, 2 and 5 obviously not equal, therefore that does not exist. Does that make sense to everybody? I hope so. Gosh, I wish y'all were able to give me feedback in real time. Okay, let's go ahead and look at another one. Now, let's go ahead and look. Actually, I'm not too thrilled with that one. That one was actually a test that I gave pre-cal students several years ago. Let's look at a couple that I pulled off of the internet today. Now, if I'm looking at these, what is the limit? And let's call this function, I don't know, just to distinguish it from the last one. Let's call it g of x, okay? So, what is the limit as x approaches -1 of g of x? what is the limit as x approaches, I don't know, let's say 2 of g of x? What is the limit as x approaches 4 of g of x? Okay, well, let's talk about all three of those in turn. Now, as the limit as x approaches negative 1 of g of x, let's go ahead and look at negative 1. Now, does the function exist there? Sure, it exists there. It actually fills it in as a point, even though it doesn't have to. It's kind of gratuitous, right? But does the function have to exist there for the limit to exist? No. It just so happens that the function exists there and has the same value as the limit. By the way, as a little foreshadowing, that's the definition of continuity. Okay, remember how I told you last year and the year before when I defined continuity, I said it was a graph that had no jumps, breaks, or gaps. And then I told you, I said, well, once we get to calculus, we'll talk about a more rigorous definition of continuity. Okay, that's the more rigorous definition. It's the fact that the limit exists, the function value exists, and they're the same. Okay, but we'll get to that when we actually get to the section on continuity, just by way of a little foreshadowing, since it's sort of germane to our discussion of sort of comparing and contrasting the limits and the function values. Now, the limit as x approaches negative 1 of g of x is going to be 4. And here, g of negative 1 is indeed 4. And if we look at it, I mean, it's right there. If you look at the little arrow mouse thingy, okay, it's right there. Now, the limit as x approaches 2 and g of 2, well, those aren't the same. The limit as x approaches 2, well, that doesn't exist. I mean, the limit from the left right here, goes to negative 1. The limit from the right goes to positive 5. Those aren't the same. So if it's not the same from the left and the right, it does not exist. But g of 2 exists. I mean, see, both of these aren't open. See, that's an open, meaning that it's non-inclusive, but that's inclusive right there, okay? G of 2 is negative 1. Okay, so here's a case in which the limit exists, but the function value doesn't. When we get to x approaching 4, or x being equal to 4, we wind up getting exactly the opposite, okay? Now, does the limit exist as x approaches 4? As I approach 4 from the right and from the left, it's approaching the same value. It's approaching 2. But g of 4 doesn't exist. It's a removable discontinuity. It's a hole, okay? So that does not exist. And here I have the strange juxtaposition of a limit that doesn't exist and a function value that does, and a limit that exists and a function value that doesn't. Just showing you that one doesn't necessarily need to exist to entail the existence of the other, and the fact that limits are about approach, whereas function values are about equality, okay? But equality was messing us up. Equality was the very thing that kept us from getting the equation of a tangent line, because it would involve dividing 0 by 0. Or it kept us from getting a exact value of the area under the curve, because multiplying by 0, you would assume to get 0 instead of getting what? An actual value, okay? So limits, approach, give us sort of the power to do things that we otherwise couldn't do. Now, let's just assume that each one of these hash marks along both the x and the y-axis are equal to 1, okay? So this asymptote right here, this infinite discontinuity, is that x is equal to negative 3. Now, one thing that I may or may not have told you last year, and in fact my memory is kind of fading a little bit, probably from the fact that I've been sitting around all day reading theology and philosophy instead of dealing with mathematics, I don't know whether I told you that there is a difference of opinion when it comes to, and we'll call this function h of x just for, just to distinguish it, the limit as x approaches negative 3 of h of x. Now remember that as far as I'm concerned, limits are about approach, and they don't, like, I'm okay with with infinity, because telling me that it approaches infinity, it's telling me that it increases without bound, it goes on forever and ever, and I'm like, cool, that's fine, okay? But for one like this, where you have a discontinuity right here, an infinite discontinuity, there are some teachers who say that that does not exist. And there are some teachers, like me, where I would actually say that that goes to positive infinity. And the AP exam, because there is a difference of opinion, the AP exam will accept either. Okay, and you're, for the sake of, you know, being in, I forget your teacher's name, but for the sake of being in her class, you're going to have to figure out which one she prefers and why. Okay, why always being very, very important. Okay, now, what is the limit as x approaches 2 here? Well, there's the difference of opinion here, but there is no difference of opinion here. The limit as x approaches 2 of h of x is going to be non-existent. It does not exist, but we do know that the limit from the right of h of x is -1, okay? And the limit as x approaches 2 from the left of h of x is going to be +1, okay? But the fact that these two are not equal is what gives us this does not exist right here, okay? Now, I hope that that is helpful in terms of sort of rehashing a graphical understanding of limits and walking through a couple of the definitions and trying to explain a little bit about what they mean and why they are stated the way that they are stated. But just remember, whenever you think about limits and get a little confused, just imagine me jumping up and down and screaming approach, 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 approach. I'm sure that that image is indelibly imprinted into your memory. Well, I hope that was helpful, guys. That was a little bit of 2.2, and that's still conceptual in terms of understanding, but conceptual by means of the graph and understanding the existence of those. Perhaps at the beginning of the next video, I will show you the delta epsilon proof, despite the fact that you probably won't have to learn delta epsilon proofs, but seeing it and not having to memorize it, just seeing it is actually rather instructive. But until next time, guys, when we will have more fun with math. See ya.